In the last class, we had discussed the analysis method for organic compound from water, and we went through the sequence of the extraction process and the analytical instrumentation. One of the concerns in chemical analysis for environmental samples is the issue of analyte losses. And this is important from the point of view of the confidence people have in the measurement. The confidence and because this is also subject litigation, the analysis that people do are used for important decisions, and therefore people would like to have some kind of confidence in terms of the accuracy of the results, and therefore the burden of the quality control and assurance and it lies with the analyst and the chemical analyst. So therefore, there are a large number of procedures that are built into the analytical procedures. If you look at a standard method that as we had discussed, these quality control and QA/QC, this is QA/QC procedures are inbuilt into the system. So in terms of analyte losses, we look at what are the possible analyte losses, where do these occur. So these possible analyte losses occur first in the transportation of the sample. Second, we occur in the storage and then in processing, and the fourth in the analytical instrument itself. Or the chemical analysis instrument part of it. So if you look at these things, we first take it one by one. We look at transport. For example, if you are taking a water sample from somewhere, collecting the water sample, so various kinds of errors can occur during the transport. And all of these categories, there are certain number of processes that can result in the analyte losses. So we will rewrite this in terms of the and these are common processes that result in losses. One of the main first things is volatilization, which is the evaporation of the sample, evaporation of the analyte from the water sample or the filter or anything. So this, whatever we are going to discuss here applies to all matrices, analysis of all matrices, whether it be water or air sample using a sorbent or a filter, or using extraction of an analyte from a sludge or soil, and it is common for all of them. So you just have to adapt it based on that. The second part of the second type of things, volatilization essentially is evaporation. We will come back to it in a little bit, how to assess it. The second part of it is reaction. This reaction could be many things. So reaction could be biodegradation. It could be reaction with other entities in the system, which things which are already present in the sample have started reacting, and over a period of time they will react. So when we say reaction, the reaction is a function of time. Yeah. So the sample, if you collect the sample at certain time and then you wait till a certain amount of time to analyze them, there is a likelihood that the analyte that you are interested is starting to react, and even if the reaction is slow, you will lose some part of it due to reaction. And this is a big concern, especially biodegradation. This biodegradation is one of the primary concerns. This reaction with other entities is what we generally we have to take care of this, because sometimes analysis itself is a problem, and then we have touched upon it briefly in the other discussion, but we will again iterate it again in this discussion. The third one is adsorption. So, the adsorption occurs to any solid surface during the processing, collection and processing, and one of the solid surfaces that you can generally see is solid surfaces we are looking at adsorption is the container itself, container of sample, collection and storage. Again, adsorption is a kinetic process, which means that if you look at the adsorption, the way adsorption occurs, the way volatilization and reaction occurs, they are all kinetic processes until there is an equilibrium. So, they will reach a point where they will not happen anymore, these processes will not happen anymore, but till that point there is continuous loss, and therefore, this influences the value of the analysis depending on how far it is from the time of collection. Okay. So, this is one of the big things. So, when you look at the design of the sample collection and the analysis processes, to reduce these three things, we take care of certain, we keep this in mind when we are designing processes for sample collection itself. For example, if we are looking at organics, there is a general theory, that rule of thumb, that organics like to bind with other organics, and therefore, the collection vessel, this container that collection and storage containers should be inorganic. In other words, one of the most common inorganic containers is glass. So, if you are handling organics, then typically it is glass containers, and similarly if you are handling inorganics, the storage and collection is organic typically, which means this a lot of times this is plastic. So, there is no adsorption, it will take care of adsorption, the other things are something else. So, if there is reactions happening, then that is something you need to take care. So, you need to find out what is your analyte and if it will react. Okay. So, there are also ways of finding out all of these things. So, I am just describing the initial processes here. So, this takes care of adsorption. For volatilization, it is very obvious. For volatilization, you need to have airtight containers, which means that the container that you bring from the sampling site to the lab for storage should be airtight, which means that there is no increase, there is no chance of this, there is no chance of loss. So, let me just explain a little bit. When we are talking about volatilization, what we are really looking at is this. Let us say a sample is exposed to, this is water plus A, this is air. So, if I take water from a river or a lake or any such place and fill this up, fill this container, there is a certain amount of air in contact with it. So, the A will move or transport and it will move until there is equilibrium, and this equilibrium is related to the Henry's constant. So, there is a very volatile compound sitting in the water. If there is air space, so it will move up. So, the general tendency is to reduce this. Your sample collection is done. So, this is also called as headspace. The sample collection is done with no headspace. Yeah. So, this takes care of volatilization. The second part is even if there is no head space, there is also a chance that this container. So, what are the typical type of containers that we have? All containers need an opening, which typically you have a bottle like this, a jar. So, the openings are usually narrow mouth. So, even if it is full, you do not need that you have a very narrow opening. So, the evaporation itself is very small. So, that narrow mouth bottles are usually taken care of, yeah. And then also the temperature is low. The temperature is low because Henry's constant is a function of temperature. Henry's constant increases with the increase in temperature. Therefore, you keep the temperature down, Henry's constant is likely to be low, okay. In addition, keeping the temperature low for sample storage and sample transportation sometimes, it will also reduce biodegradation if there is happening. So, all reaction, all biodegradation typically is low when there is at low temperature. So, this is generally the rule of thumb, that sample storage and collection is happening at low temperature. Sample transport and storage. Yeah. We talk about adsorption. One of the main things that even if you use a glass vessel, sometimes there may be adsorption. The glass vessels may have dust, and the dust can be organic. So, if you are looking at an organic chemical analysis, and adsorption occurs on the dust and the cap of the vessel. So, you have this kind of a cap. The cap is usually made of plastic. The reason it is made of plastic is we need an airtight seal, and to get an airtight seal, usually it is, you can get an airtight seal only if you have some kind of a washer or something like that, and that is usually these materials are plastic or polymers. And so, there is a chance of, so one must take care that if you do not want any loss by adsorption, you must use a clean glassware as well as use very small amount of plastic, or as far as possible use an inert plastic. So, inert plastics means that these plastics do not interact with many things. So, there will be adsorption, but adsorption is minimized to a large extent. So, there are many plastics that are available that people make these caps with, the lining of the cap. So, the inner lining of the cap. So, the inner lining of the cap is this portion where this is the screwing mechanism, the screw cap mechanism is here. So, this is a plastic cap, and the inner lining, there is a lining, there is a plastic liner. So, this plastic liner is to an extent made. You also have aluminum liners and all that, but their problem is that they may not be very tight. So, people are trying to make containers that are as best as possible, because samples in the sample transportation and storage, there is a possibility that the bottle will get upturned. If you do not want to do it at all, you do not want to take care that absolutely there is no contact, then one can ensure that the bottles are not turned and they are upright throughout, and that one can take care. But a lot of times one is not sure whether this is possible. Sometimes sample storage and sample transportation, it is not possible to keep bottles upright, and it will happen. So, this is all to take care of those kind of issues as well. Okay, so we know that there are these losses. So, when you do an analysis, how do you check? How do you check for these losses? Can we ask this question, can we measure or estimate analyte loss? And the answer is yes, and we do it the same way we do, since this is a type of measuring the accuracy of the sample. The only way we can check accuracy is by using a standard, So, one of the two things So, when you are doing analyte loss, we are assuming that that there is a certain amount of material that is going out of the system. So, the only way to do that is you know what is there in the sample originally, and then you find out what you can recover. So, we measure. So, this is a sequence of sampling this thing, right? We get sample, collection site. This is a recap of what we do. Sample processing and analysis. So, the analyte goes through all of these stages, and therefore, in each stage there is a loss, there can be a loss. Especially when we are doing extraction by a solvent and all, and then we are concentrating the solvent. We can have a lot of volatile losses because some of these solvents are volatile, they are meant to be volatile because you need to concentrate, they must be easy to evaporate. During the evaporation they will also release some of these chemicals, the analyte also may go along with it. So, it is fair to expect that there is a fair amount of loss. So, if I put 100 milligrams per liter of a sample, if the analyte contains analyte concentration in the sample is 100 milligrams per liter for say, and by the time you come to the analytical instrument and the instrument reading gives 70 milligrams per liter, it means all it means is that there is a 30% loss in the system. Yeah. This 30% loss in the system, if you do not know that, if you do not measure this, that there is 30% loss, you will assume that 70 is a correct number, and so you are underestimating a pollutant concentration. From an environmental analysis point of view, this is not a good thing, because underestimating the pollutant concentration is not safe, and therefore, one would rather overestimate it because it is still conservative, but underestimation is a problem. So, we would like to measure it. So, the easy way, one way is to check the loss. So, is to check the recovery efficiency, the percentage recovery. So, we define recovery as a measured concentration by true concentration. This is the recovery, this thing, this percentage recovery is into 100. This implies that the true concentration equals measured concentration divided by recovery, percent recovery by 100. Yeah. So, for example, if recovery, in this case, if recovery is 70%, therefore, the true concentration, the true value is measured value divided by 70 by 100, 0.7. Okay, this is usually this is the calculation one does. So, how does one measure the recovery? One method that is available is by doing what is called as a laboratory control sample. What we do here is we take the matrix. So, in this case, let us take the case of water. We take water, we add a known amount of standard into this and let it go through the entire sample storage. So, we add it and we take it through the transport, storage, processing and analysis. So, we know what we are adding. Let us say that we are adding so that this concentration is known for us, known say it is 10 nanograms per liter or something like that, and then we run it into the instrument and we get finally we get a concentration of 8 nanograms per liter. Okay. We calculate what is the concentration in the extract based on the GCE, we discussed it in the previous class. So, we know now that the recovery is 80%. Okay. Now, we assume that this recovery applies to all analysis done in the same manner, same method. So, if you are not changing the method or not changing the time it takes, then the recovery is assumed to be the same, or we do it several times and we have an average, we have a mean recovery and then we apply it to all samples as a correction factor for the analysis that we do. There is a problem in this, it is not accepted. This is the easier way to do it, because you can take the analyte of the standard of the analyte itself and do it. So, it is exactly the recovery of that particular compound. However, the general criticism or the drawback of this is that it does not take into account what is called as matrix effects. What we mean by this is that the water itself, say we are taking sample from a lake, the lake water may contain other constituents that may influence the analysis, that may influence the way in which extraction is done and the way influence the concentration and this. So, by doing a laboratory control sample, we do not take into account all of these. So, we need to take this matrix effect, which we need to use the same type of water. How do we make the same type of water? Very, very difficult, and we get into more trouble by trying to replicate that kind of water. So, the second option that you have is use the actual sample matrix. But this leads to a problem that if you use the same sample matrix, then how are we going to, if you add the standard of this particular analyte into the water, you do not know what exactly is present in the beginning. So, for example, let us say I have 80 nanograms of A that is already there in the sample, to which I add 80 nanograms of the standard. I extract and I end up with say 100 nanograms in the final extract. I have no idea of knowing if this 100, so if it is 100, then of course I have a problem. It is greater than 80, which is a standard addition. So, I do not know how much of this loss, there is a loss from here and there is also a loss of this, and I do not know which one, because I do not know this number. If I know this number, I can find out, yes. Because I do not know this number, I do not know how much of this is loss is coming from here and here. Therefore, I cannot do that because it is the same compound, a compound may be there. So, this can work if the standard that you add is not present in the sample. Okay. Now, you have no a priori no way of finding out, but you have already some guess that what you are looking for. So, it is a very tough situation because it is difficult for us to find a compound that is not the analyte, but it is close to the analyte. Okay. This is where we get to the definition of what is called as a surrogate standard. A surrogate standard is usually a compound that is very similar to the analyte of interest, but it is not the analyte of interest. And so, in the analytical instrument that we are using, this shows up around the characteristics similar to, most of the time we are using chromatography. So, it shows up in the chromatogram, but not at the same point as the analyte, but it shows slightly off, especially in methods like GCMS. Okay. So, what we are looking at is typically things like radio label compounds. For example, if you are looking at naphthalene, okay, so that is 2 benzene rings. The radio label part is either replacing, one C12 by C14 or replacing one H by deuterium 2, some such thing. So, one atom is replaced by an isotope, and so these isotopes are not part of, they are not present in the environment, and they also show up a signal that is slightly different from the non-radio labeled naphthalene. So, this being the case, since this is, if this is the case, then one of the things that we do is we are able to distinguish between, in these two cases, which is the sample. The sample is, we get a signal of naphthalene, we have some value of naphthalene, but we know the value of the radio label standard that was injected and radio label standard that was extracted. So, we use the extraction efficiency or the recovery efficiency of the surrogate standard and apply it to all compounds that are nearby. The reason I am saying this apply to all compounds is surrogate standards are expensive. Surrogate standards are expensive, and therefore, if we are analyzing 100 compounds in a series in a water sample, we can't, it is difficult for us to buy 100 surrogate samples, it is prohibitively expensive. So, there is one surrogate for a set of compounds, and we apply that, then we, for the next set we buy another surrogate standard and we apply that. So, it is not the best way to do it, but it is close. The third method is called as a matrix spike. In this, we take a sample, we split into two smaller samples. Into one, I add a normal standard. If I add the analyte A standard, this is not a surrogate, this is, and the other I do not add the standard. So, this has analyte plus standard, these are only analyte, and this both of these samples go through the analysis, and then the difference between these two, so difference between these two will reflect the efficiency of the extraction of one of the standard that you have added. Okay. So, what this does is, this is a better way than using a surrogate. The only problem here is again that you are splitting the sample, and that is additional analysis, is one additional analysis that you have to do. So, you have to work out the overall cost of doing it by doing it, but you do not have to do it often, you do it once in a while just to check if there are matrix effects on this. So, these are the three methods. You have laboratory control samples. With a standard addition, we have a surrogate. And we have the matrix spike. Sometimes they are talking about sample losses. There is also another aspect to sample losses lead to underestimation, which is usually falls under the category of false negative. But there is also another case of false positives, which means that what we are calling as false negative is not just the whether it is not a true false answer. We are saying false negative essentially means it is an underestimation. It is another way of representing a false negative, that is, you are assuming that something is not there when it is there. So, you are neglecting that missing component. Similarly, you have false positive, which means we are overestimating. And this can happen if you have sample gain. So, sample gain is fairly, it seems non-intuitive because sample is loose. Where can you gain sample from? So, mass cannot be created from nothing. So, there are a few instances where you get sample gain, and the sample gain happens, the sample gain we are talking about mean by addition of the analyte from somewhere. addition of analyte in the sample not at the collection site but somewhere else by an artificial mean. So, how does this happen? This happens by several means. One is the most common contaminated apparatus. This is a very general case. Apparatus could mean, very simply, it could mean dirty glassware or containers, dirty transfer equipment. So, for example, during the analysis and extraction you transfer, there is a lot of transfer that is happening. In that there could be, you use a pipette for a higher concentration and you dip it into a lower thing, and that is contamination. It can transfer material from a higher concentration to lower concentration, that is a problem. Yeah. Dirty instrument, this is a very common way of things happening. Dirty instrument means the analytical instrument is not lost its previous sample. So, I inject a sample into a gas chromatography instrument and it retains some of these chemicals from one analysis, and that is sample loss for one sample, but for the next sample it is sample gain. So, both these things can occur, this kind of instrument loss, in the case of an instrument thing. So, this is usually called as sample memory for instruments. So, there is a lot of very strange things that happen, because when you have sample loss, all of these adsorption and volatilization, all of these are happening, are driven by equilibrium, which means that material always moves from a region of high concentration to low concentration. So, if the sample matrix, if your analyte is in a matrix in a medium that is at higher concentration than the one which is in contact with, it will try to go adsorb there. But if you have a sample with a lower concentration than whatever is the contamination, so therefore, if there is a channel in which the analyte is adsorbed, if this concentration on the solid is greater than the concentration in the liquid, then the transfer will occur this direction, which means it will release chemicals into your sample. So, that is a false positive. Your concentration is being gained by this. So, how do you check for this? The checking for this is why we use what is called as a blanks, and we have discussed this in other lectures. But the blank analysis is very important, because every time we do an analysis we need to do blank, and this blank can also, dirty glassware apparatus, we also have the other category of dirty solvents. What we mean by dirty is contaminated, that is the correct word for it, because in the lab where a lot of analytical work is happening, there is always a possibility of cross contamination, and this is a very real way to do it. So, the matrix itself, the clean matrix, you need a reference for a clean matrix for doing a blank, which means that, so I need to do the entire analysis. So, blank analysis usually will occur where I need to do the entire analysis. So, I take clean water and go through the analysis through the entire thing, and then I get a reading or a measurement. If this is greater than 0, which means that system is contaminated, you cannot do any further analysis until this becomes close to 0 or insignificant, below detection limit. In other words, the correct word is greater than the minimum detection limit. Okay. So, this is, I think there are two, to summarize, we need to estimate recovery for losses, we need to do blank analysis for gains, sample gains. Sample gain can also happen by contamination of the sample itself. For example, if we are contamination of sample, we are looking at dirty, we are also looking at things like deposition. This does not happen to all sample, deposition of material from exposure to air. Can also happen by reaction, but that is very rare. You usually do not, it is a rare coincidence where the analyte you are interested in is coming from a reaction of other things present in the system leading to this. So, that is usually very uncommon. But this deposition from material exposure to air is common and it is important in some cases, especially when the component that you are looking for, interested, is there in the environment. And this is most commonly, this deposition of material from exposure to air is most common in the analysis of elements, metals, elements, because there is a lot of dust which is, for example, you are analyzing soil or water from a lake or a river. There is also a lot of material which is there in the ambient environment which can deposit in and that will give you a wrong reading in that case. Okay, so to summarize this, there is recovery for losses, there is blank analysis for this thing. There are different kinds of blanks. There is a method blank. These are all methods of troubleshooting. There is a method blank that essentially tells you if along the way there is any contamination that is happening. Yeah. There is an instrument blank which tells you if only the analytical instrument is causing a release which is causing an addition. Then there is a solvent or the matrix blank. So these are all troubleshooting methods in which you see some sample, you see some additional thing, blank is not clean, then you try to find out which part of the process is dirty and then find out. Okay. Similarly, even for the losses, you can run the standard, you can run it, you can do different kinds of recoveries, you can do the introduction of the chemical all the way back at the sample, or you can introduce it at different places to check where the significant loss is happening, so that you can correct for that if possible, especially if the loss is very big. Okay. So, in general, the QA/QC procedures, summary of the QA/QC procedures, we need the first and foremost we need calibration with standards. Then we need what we call as replicates for repeatability. Now, this is repeatability of the entire process. So, which means samples, we must take sample replicate that will indicate several things. Sample replicates indicate the heterogeneity of the sample itself. It also indicates if your analysis procedure is consistent. So, every time you do it, you should get similar results. So, that is the repeatability of it, which means you have more confidence in your results. This is expressed as the calibration with a standard which will give you the indication of true value and how far it is from that. Repeatability is expressed as an error bar. The people look at error bars and then tell you how close the values are, that is one thing. Then we have to do a series of blanks. So, every time you start an analysis, you start with a blank and then you start with the standard. Then we do a recovery with many of the this thing. Yeah. In some cases, we also use what is called as an internal standard. It's not done in a lot of methods, it's done in only a few methods where there is the instrument, the way the instrument processes the sample analyte is a bit, there is a lot of uncertainty in that, and therefore, in order to track what the instrument is doing, and it changes as samples are being processed, the sample process. So, this happens in a few instruments like the ICP MS. This internal standard, we are not going to discuss it in detail, but all it means is that just like the surrogate, we add one internal standard to every sample and we track the ratio of the internal standard to the actual analyte, so that we know whatever loss is happening to the internal standard is applicable to the analyte of your interest also. So, I think this covers the a major QA/QC portion for chemical analysis, and this applies for everything. So, if you go and look at a standard method, there is a large section on QA/QC which covers all of this and gives recommendations as to which surrogate standard to use, which internal standard to use, and people have done a lot of work on different methods, analytical methods, and this analytical methods works for all matrices, it not just for water or air or filters or sediment or sludge, it works for everything. If you are developing a new method also, you need to look at procedures, quality control procedures to incorporate all of these things.